Okay guys, let's talk about quantum numbers. We are going to do this again in class, but I thought it might be good for you to have some kind of a record in case you forget what we talk about in class. You can always come back here and look at it, and it gives us a nice little review. So, we are going to talk about quantum numbers, and so if we look at the atom helium, or hydrogen has one electron, and since it is the lowest or the very first atom we're going to deal with, n must be equal to 1, which means L can only have the value of 0, which means then M can only have 0 as well. Since it's our first electron, we're going to give it the quantum number of plus 1/2. If I were to do that in a line notation, it would be 1s, and I would put one arrow going up. So, helium. Helium has 2 electrons. The first electron is exactly like the one for hydrogen, but what about that second electron? Well, since I only put one electron in there, I would have 1s, and now it would have 2 electrons. Now I can describe the second one, keeping all of these 3 quantum numbers the same and just changing this one. So I'd have n equal to 1, L equal to 0, M equal to 0, and S would be minus 1/2, and that's denoting the second one that's going down. How about lithium? Lithium has 3 electrons and would still, now if we look at it, we're going to have our electron configuration is, and I didn't write that here, 1s2, 1s1. This would be 1s2, and now I have a third electron, so I have to go to the 2s, and I put 1 electron there. What would its line notation look like? It would be 1s with 2 arrows, and then 2s, and again, we always put the first one going up. So, this would be the first electron, this would be the second electron. What does that third electron look like? Well, n now has to equal 2, but I can still use L, and I always start with the lowest value of L anytime I start a new n, so I would start L equal to 0, which means M equals 0, which tells me again I have an s orbital, it's in the second energy level, and I have to put plus 1/2 because I only have 1 electron in there. Beryllium has 4 electrons, and it's 1s2, 2s2. So, my first electron, second electron, third electron, what does the fourth one look like? Well, n would still equal to 2, because I'm in that second energy level. I still have space for one more electron here, so I can still use L equal to 0 and M equal to 0, and this would be minus 1/2. And so my electron orbital line diagram would be 1s2, or 1s with 2 electrons, 2s with 2 electrons. What about the next one? What is our next element on the periodic table? Doesn't really matter. We have 5 electrons. It would be 1s2, 2s2, and now 2p1. Here's the first 4 electrons, and n still equals to 2. Now L has to change. I can't write another configuration with the values of L and M that I have. So if we look on our periodic table, that element actually is boron. We have N equal to 2. Now L is going to equal 1 because I'm now into a p orbital. And M can be either -1, 0, or +1. And we always start with the lowest value, so it would be -1. We used to always start with plus 1/2. Our orbital diagram would be 1s with 2 electrons, 2s with 2 electrons, and now we have 2p, we have 3 orbitals, and we just put 1 electron here. After boron comes, I know this is getting boring, carbon, 6 electrons, 1s2, 2s2, 2p2. This actually will show us how the Hund's rule comes into effect, right? Where we want to keep them unpaired as long as possible. So now 2, 1, here we're going to use 0 now. We're going to use that second value for m, and we're going to stay with plus 1/2. And so we get 1s, 2 electrons, 2s, 2 electrons, 2p, with 1 going up here and 1 going up here. So again, we'll do some more of these in class, and you'll get to do lots of electron configurations. I'll have a video on that as well. Thanks.